we've got two functions here that I'm purposely making kind of close together. So the region between these functions is fairly small. I could have come up with an example where it's bigger. But this will illustrate a certain conceptual point. The top graph is going to be the graph of y equals x squared, and the bottom graph is going to be the graph of y equals x cubed. When x is between 0 and 1, I hope you know, if you take a number between 0 and 1 and cube it, you get actually a smaller number than if you square it. For example, 0.9 cubed is 0.729, but 0.9 squared is bigger, 0.81. So x squared is actually above x cubed on this interval. What I want to do is I want to take this region between these two functions and rotate it to make a solid. Most commonly, you would rotate around maybe the x-axis here or the y-axis. But to make things a little trickier, sometimes we rotate around some other line. What, a slanted line? You could do that, but that's really tricky. Let's make it be the line y equals -1. To start with, we'll also do x equals -1. What kind of solid am I going to get if I take this two-dimensional region and rotate it around that line y equals -1? It's kind of tricky to try to draw it. I could draw sort of another piece of it down here. That's kind of the mirror image of that piece up there. But you also have the part in between. You are doing a rotation, so it's some sort of object that is obtained from a rotation and is solid. It's got a certain thickness to it because there's a certain distance between these curves. You could say there's a part where you rotate the top around and also the bottom around. It's difficult to draw this very accurately. What I'm after in finding the volume of this is not the volume of what's inside. Pretend this is a horn, well, with a really big mouthpiece. I can't open my mouth very wide. Horn with a really big mouthpiece. We're not talking about the air inside and what's its volume. We're talking about the material to make the horn that does have a certain small thickness to it. Maybe you make it out of wood, maybe out of plastic. How much wood or plastic do you need? Let's pretend the length is in centimeters this time. If length is measured in centimeters, I'm after the volume then in cubic centimeters, but it's going to be a pretty small volume because it again is the amount of material based on the thickness here. And so it's a very thin thickness. So it's a very small amount of volume of material that you need to make this thing. And we're not talking about the air that's inside. What do? Get out your knife, slice it. How? You want to slice it in such a way that the cross sections are simple shapes. It'd be bad to do it this way. It'd be bad to do it this way. This way is better. If you think about it carefully, the cross sections seem to be somewhat circular in shape. I'm drawing this with perspective, so it looks like an oval. But you need to imagine the circle going into the paper. It's a circle, well, with a certain amount of thickness to it, which gets difficult to draw. What is the cross section here? It's the region between two circles. That's what an arbitrary cross section looks like. This region between two circles. You might use different words to describe it. You might call it a ring because it looks like a ring. You might call, well, the more official mathematical name for a ring is an annulus. Or if you're more of a mechanical mind, and I don't mean the class mechanics, but I mean literally like fixing cars or doing plumbing, you might think of it as a washer, right? Like a washer for a screw, or a washer that you put in your faucet to try to prevent leaks, which me and my wife are having a lot of trouble with our leaky faucet in our kitchen right now. We've tried fixing it a couple times. It's been fixed for like a week and then it comes back. Leaky faucet. So you could call it any one of those things. That's what you'd see if you were if your eye was over here and you're looking toward the right, or toward the left, excuse me. You'd see this kind of shape. This does have a certain tiny width in the x direction, delta x. That's the tiny width. The area of the cross section is not part of that width. But if I multiply that area times the width, I get the approximate volume of the cross section. The sides of the cross section, taking into account the width, are not horizontal. They're slightly slanted. They're slightly curved even. So in multiplying the cross-sectional area by the delta x, I'm not getting an exact volume of the thin slice, only an approximate volume. But the approximation gets better and better the smaller delta x gets. And so that's a pseudo justification of saying that in the limit as delta x goes to 0, we're ultimately going to get the integral. Yeah, we could write delta v, the tiny volume of the thin slice of width delta x, tiny width delta x, is approximately the cross-sectional area, I'll call it A of x, times delta x. I'm not going to figure out A of x right away, just like in the last problem I didn't figure out A of y right away. The total volume then of the solid is the sum of the little volumes, which would be approximately the sum of values of A of x times delta x. In the limit, as you let delta x go to 0, you could think of it as a definition, or depending on how you approach things, a theorem, to show this, the volume then ends up equaling the integral of A of x over whatever interval that x is ranging over, varying over. It's going from 0 to 1. Look at the picture. That was a 1 there. That's a 1 right there. X goes from 0 to 1. That's your limits of integration. In the infinitesimal approach, here's the infinitesimal version of this approach. You'd write dv equals A of x dx. You'd go to this equation, this approximate equation, change the deltas to d's, change the approximate equation to an exactly equal to. You might say this is semi-rigorous math here in the standard real number system, but this is not rigorous math at all. This is a convenient fiction. Don't write a summation sign in the usual sense of the word. Instead, say the total volume is the sum of the little volumes, where the integral sign is your sum. Then get to your integral that you actually calculate by saying, hey, I guess I need to replace dv with how it depends on x. And I guess I also need limits of integration if I'm actually going to do the integral. Hand wavy. Right? Feels like magic. Poof. That's what you do. It's when I say that it's just in fun, okay? But there's a serious side too, because you do want to get the right integral to do, and you do want to get the right answer. Right? I mean, if you're doing pandemic modeling, dare I say, okay? Like that people did with COVID, and you get things wrong, maybe more people will die. And that literally happened, possibly with different approaches. I'm not going to get into the politics of it. You know, different assumptions you make, different approaches. If you do it wrong, it could lead to bad prescriptions. So there's a serious side to this, is what I'm trying to say. Even though we're trying to kind of have fun with it in thinking about it with these different ways. But it still begs a question, what is A of X? Again, A of X is, well, not the volume of this, but the area of the cross section. It's the area of the region between two circles. One with a smaller radius than the other. You could call the radius of the inner one Rn for inner circle, and the radius of the outer one R out for outer circle. And the area of the cross section would be the area of the outer circle, pi R out squared, minus the area of the inner circle, pi R in squared. So is this my A of X? Is this the function that I integrate? Not as it's written, it's not, because I haven't simplified it in terms of X. I'm not even saying R out and R in depend on X, though they do. This thin ring shape gets bigger and bigger as X gets bigger. How do R in and R out depend on X? Tried to draw a little bit more in the picture. This line here, for example, at a given value of X, going from y equals -1 up to not the x-axis, but a little further. Watch where my pen is. The curve, x cubed. That's R in, that distance. It doesn't equal x cubed. It equals x cubed, this distance, plus 1, this distance. Or if you want to take x cubed and subtract -1, you get the same thing, x cubed plus 1. R in is a function of x. It's x cubed plus 1. If we were rotating around just the x-axis instead of the line y equals -1, then R in would be x cubed. The plus 1 comes from the fact that we're rotating around the line y equals -1. We have to add this extra distance of 1. The outer radius is something similar, except you got to use the curve x squared. It's the distance between the x-axis and this point right there. Add on 1 to that. Our outer is bigger when x is between 0 and 1. It's x squared plus 1. Combining these things, we see that the A of X function, going back up here, I could factor out the pi. There's a factor of pi in both spots. It's pi times, in parentheses, R out squared, which will be x squared plus 1 quantity squared, minus R in squared, x cubed plus 1 quantity squared. And that's the function we'll have to integrate. Let's simplify it. Square these binomials. I have to FOIL in my head. X squared plus 1 squared will be first times first is x to the 4th. Both the outside and inside products are x squared, so I get 2 of those. Last times last is 1 squared is 1. Subtracting this thing squared, FOIL that, x cubed times x cubed is x to the 6th. Both the outside and inside products are x cubed, so I get 2 of those. And last times last is 1. Distribute the minus sign through the parentheses. The 1s will cancel. And if I decide I'd like to put the powers in descending order, I'm going to have a negative x to the 6th, plus x to the 4th, minus 2x cubed plus 2x squared. Do you see what I did there? I just Switched around the order a bit. Going from high degree to low degree. You don't have to do that, I just did. Getting close here, that means the volume is going to be the integral of that. Factor the pi out. Pi times the integral from 0 to 1 of what I've just written here, negative x to the 6th plus x to the 4th minus 2x cubed plus 2x squared. This integral is not as hard to do as you might guess initially because of the 0 to 1. Get my antiderivative. Looks like we get this. Evaluate from 0 to 1. The only thing that's going to give me something non-zero is when I plug in 1. And when I plug in 1, 1 to any power is 1. Effectively, I just have to add these fractions because of all the 1s. What's a common denominator? 2 times 3 times 5 times 7. 210 is a common denominator. Let's see. 1/7 as a fraction over 210 is 30, 210. So I also have a negative sign. 5 goes into 210 42 times, so I get a plus 42. 2 goes into 210 105 times, so I get a minus 105. And then 2/3 is the same as, what would it be here? That's divisible by 3, 140 over 210. 140 minus 105 is 35, plus another 12 is 47. 47 pi over 210. My original length unit was centimeters, so this would be in cubic centimeters. And I did approximate this in the last class with my calculator. It's about 0.703 cubic centimeters. Not very big, not a very big volume. That should not be surprising because it's the volume again of the material, not what's inside of this sideways, this horn shape. There's not much material that's needed, only about that many cubic centimeters. I could have rotated this same two-dimensional region right there around this way, like the y-axis, or maybe the vertical line at x equals -1. I don't have enough paper to draw the whole thing, but imagine with me doing that, what would I get? I'd get a bowl shape, actually, instead of a horn shape, although the bottom of the bowl would have a big hole in it, and so if you put cereal in the bowl, it would fall out. Once again, I'm after the volume of the material, which should not be very big, not the volume of what's inside the bowl. So if I try to find the volume of such a solid there, I should still get a small answer. Will I get the same answer as this one? I hope it feels like it probably would be different, because different width regions are getting rotated different distances, you might say, than they were when we did it this way. I mean, the differences might be slight. What are the cross sections in this case? They are once again same shape. But instead of looking to the left to see those cross sections, you'd be looking downward to see them. You'd still get this ring shape. The area would still be pi times the outer radius squared minus pi times the inner radius squared. What would change? You'd be doing it with respect to y instead of x, because your sections are perpendicular to the y-axis. Y is what's changing in that case. So it'd be with, I'd have to figure out how these things depend on y instead of x. Integrate as y goes from 0 to 1. What? X cubed minus x squared? No. You have to figure out how these things are functions of y as well. This one is x equals square root of y. Y is positive here. Same as y to the 1/2. And this one is x equals cube root of y. Y to the 1/3. Those are going to be the functions that I need to figure out my inner and outer radii. I also do have to add 1 to them, to that distance right there, just like before. Again, if I was doing it just around the y-axis, I'd get a smaller bowl shape that would not have a hole in the bottom. I would not add 1. So what will I get if I do it that way? I won't bother writing down the Riemann sum or the infinitesimal version. Let's just write down the a of y function. Pi times the outer radius squared minus the inner radius squared as functions of y. Be careful. You can see in this picture now, if you're measuring distances horizontally, the outer radius, the bigger one, goes to the cube root function, and the inner one goes to the square root function. So it's going to be, outer radius is going to be y to the 1/3 plus 1 squared. Inner radius is going to be y to the 1/2 plus 1 squared. That's r sub out as a function of y. This is r sub in as a function of y. Squaring them, subtracting, and multiplying by pi. Before we integrate, let's simplify. Even though it's a 1/3 and 1/2 power in those binomial expressions, you can still square it with foiling. That's still possible. Y to the 1/3 squared is y to the 2/3. Outside and inside products give me 2 times y to the 1/3. Last times last gives me plus 1. Subtract this thing squared. Y to the 1/2 squared is y. Outside and inside products give me 2 y to the 1/2. Last times last is 1. Like before, the ones cancel. If I write this in descending powers of y, the highest power is y to the 1st. The next highest is y to the 2, with a minus sign, excuse me. The next highest is y to the 2/3. Then minus 2 to the y to the 1/2. Then plus 2 y to the 1/3. That's my a of y. That's the function I have to integrate. So this volume of the other solid obtained by a horizontal rotation about a vertical axis at x equals -1 is the integral of this thing from 0 to 1. And it's definitely doable. You get pi times, in parentheses, -1/2 y squared plus 3/5 y to the 5/3. Do you see that? 2/3 plus 1 is 5/3. Dividing by 5/3 is the same as multiplying by 3/5. Here, 1/2 plus 1 is 3/2. Divide by 3/2 is the same as multiplying by 2/3. Times 2 is minus 4/3. Y to the 3/2. 1/3 plus 1 is 4/3. Dividing by 4/3 is the same as multiplying by 3/4. 3/4 times 2 is 6/4 or 3/2. Y to the 4/3. Plug in 0, you'll get 0. Plug in 1. 1 to any power is 1. So same kind of thing happens as before. We need a common denominator. It looks like we want to use 2 times 3 times 5, which is 30 for our denominator. -1/2 is -15 over 30. 3/5 would be 18/30. -4/3 would be minus 40/30, and plus 3/2 would be plus 45/30. 45 minus 40 is 5, plus another 3 is 8. Yeah, 8 pi over 30, or 4 pi over 15 cubic centimeters. I approximated that with my calculator in the last class. It's about 0.838 cubic centimeters. Slightly bigger in volume than the other example.